Functional analysis distinguishes between two worlds. In finite dimensional spaces, we find a high degree of predictability, but as we move into infinite dimensions, that stability often disappears. Limits can vanish, and sequences that seem to converge may suddenly lack a destination. This progression shows how we build these environments. We start with a vector space, where we define how arrows add and scale. Adding a measurement tool turns it into a normed space. Finally, we establish completeness, a Banach space, where we ensure that every sequence heading toward a limit actually finds one within the space. We define a subspace by its algebraic behavior. While a subset is just a collection of points, a subspace must be closed under addition and scaling. If you combine any two vectors on this plane, the result remains on the plane. This plane is finite dimensional because its entire surface is generated by a fixed set of basis vectors. Every point here can be described as a specific combination of these two directional anchors. Relying on a finite basis ensures that the geometry of the space is governed by specific, predictable algebraic constraints. To prove why these spaces are stable, we examine vectors and their coordinates. A target vector is formed by two linearly independent basis vectors. Because they point in different directions, they cannot cancel to zero unless their coordinates are zero. Length stays proportional to its parts. This property leads directly to Theorem 2.4-2. Every finite dimensional subspace is automatically complete. When a sequence of vectors clusters toward a limit, the lemma ensures their underlying numerical coordinates are also clustering. Since the real and complex number lines are complete, the entire finite dimensional space inherits that completeness. Every converging sequence is guaranteed to reach a limit. Following this, Theorem 2.4-3 establishes that these subspaces are closed. Their limits cannot escape the boundaries of the subspace. Contrast this with an infinite dimensional space, like the space of continuous functions. Here, a sequence of polynomials can converge to form an exponential function. In this case, the limit is a different class of function than the terms that created it. While infinite dimensions can leak limits in this way, finite dimensional spaces remain contained. The stability of these spaces extends to how we measure them through equivalent norms. If one norm can be bounded within multiples of another, they are considered equivalent. This grid shows two ways to calculate distance. The circle represents the Euclidean norm, straight line distance. The diamond represents the taxicab norm, measuring distance along grid lines. We scale the circle down to fit inside the diamond, then scale it up to enclose it completely. This sandwiching is the basis for Theorem 2.4-5, which states that in a finite dimensional space, all norms are equivalent. Because these different measurement tools are mathematically linked, a sequence that converges to zero in one norm will necessarily converge to zero in all others. Convergence is a property of the space itself, not just the ruler we choose to use. These three pillars define the finite dimensional experience. We have completeness to prevent missing limits, closeness to prevent limits from escaping, and equivalent norms to ensure consistent measurement. These properties hold because the geometry of the space is entirely determined by its finite set of basis factors. Mastering these concepts provides the necessary foundation before exploring the more complex and often counterintuitive behaviors of infinite dimensional spaces. If you found this deconstruction of finite spaces helpful, please like the video and subscribe. Leave a comment below letting me know which area of functional analysis we should cover next.